thanks a lot for accepting the invite and welcome on Wall Street Talks. Is a pleasure to have you on board. And guys, the host we have today, Mounir, is an expert on nuclear fusion. So it's really interesting to talk with experts like you. I'm sure it's gonna be a great talk, and I'm gonna learn a lot because most people listen to this podcast, and me included, don't have a background in physics or not even talking about nuclear fusion. So it will be very interesting to have a talk to you and with you. And please just be, talk to us. You're not talking to your PhD friends. So yeah, we're gonna make it easy. Why don't you spend a minute like presenting yourself and a little bit of your background?
Of course. All right. So thank you, Andrea, for inviting me. It's always a pleasure to talk about nuclear fusion, as it's, one of the big achievements which are currently being happening. And so my name is Mounir. I did a bachelor's degree in Lebanon at the Lebanese University, and then went to France, where I'm currently finishing my master at Aix-Marseille University. And currently I'm at the Swiss Plasma Center of EPFL, where I'm doing my master thesis internship. So my research has mostly been on plasma physics and nuclear energy so far, mostly on the topics of plasma material interactions and plasma waves interactions. These might be a bit too technical for the public.
Yeah, and just to translate, plasma waves interaction is about what?
Yes, so basically the plasma is the fourth state of matter, and it's actually the state that we're going to use for these fusion reactions, right? And so we know that inside this plasma, some waves basically are able to propagate inside, which might interact with the plasma and transfer some energy to the plasma, but although the plasma might be able to transfer some energy to these waves. And the goal of plasma waves interaction is basically to understand how this interchange can happen and towards what can lead, basically.
Okay, that sounds amazing. Great. So I was looking, I was getting interesting in nuclear fusion actually by I heard of this quite a long time ago. We have been talking about this for quite some times, and doing some research, I found that the first theoretic idea of nuclear fusion came out in 1915, and has something become real, and why has it taken so long? People know that nuclear reactors exist, and nuclear fusion is not nuclear fission, which is used currently in nuclear reactors. Why has it taken so much long? And for someone that is outside, would say like, why is it possible to do it with one method and not the other yet?
Yes. Okay, that's a very, very good and fair question, actually. But I think before being able to answer to this question, let's maybe introduce the public to the background of what nuclear fusion is, and then maybe talk about some of the challenges that we're currently facing in the community. Maybe that's
a great idea. Yes.
So before answering this question, I would like to make a very small reminder for the public about the structure of the atom itself, right? So the atoms are basically what everything in the universe is made up of. And if we take an atom from a particular element, its internal structure essentially consists of a nucleus containing subatomic particles called protons and neutrons. And around this nucleus, you have what we call the electronic cloud, where the electrons rotate around this nucleus. And so now going back to nuclear fusion is basically the underlying process that powers the universe. So as the name implies, it fuses together or brings together two different elements, technically nuclei, that come together. And if you can push them together close enough, you can trigger essentially a reaction. What happens is that the elements typically change. So this means that you change from one element to another. through an internal modification of this chemical structure. And now this rearrangement of the chemical structure through the famous equation E equals mc squared, which you guys, I think you've probably heard of this famous equation, releases large amounts of energy. So fusion is the fusing together of lighter elements into heavier elements. When you go through it, you start from, let's say, some initial elements, typically hydrogen, and they have a particular rest mass, like a mass basically. But the rest mass is like the fancy scientific term that we use when we want to talk about something that do not have any kinetic energy, which is still at rest, right? So we start from elements that do not have any kinetic energy and have a specific rest mass. And when you look at the product afterward, it has less rest mass. And so you say, oh, well, how is that possible? Because you have to keep the mass. But mass and energy are the same thing, which is what E equals mc squared means. And this conversion of this mass comes into kinetic energy, namely energy that can be exploited in some way. And all this mechanism, this is what happens in the center of stars, like our sun. So fusion is literally the reason life is viable in the universe. Now, on the other hand, you have what you mentioned about nuclear fission, which actually relies on the same underlying physical principle, but it's exactly the opposite, which is actually what the names imply. So uranium-235 is one of the heaviest unstable elements. And what happens is that fission is triggered by the fact that one subatomic particle, like the neutron, which I previously mentioned, has no electric charge. And basically, if one of these neutrons comes and gets in proximity enough to this uranium-235, it triggers an instability. An instability from the inside of the nucleus of the atom and splits it apart, which means that it changes it from one chemical element, to like a whole array of lighter elements and nuclei. And when that happens, there is, as in a fusion reaction, less rest mass left than the original one at the end. And so it's actually the same. It's a rearrangement of what we call the strong nuclear force, like the conversion of mass into energy. But basically in the reverse process. So we're taking the heaviest elements instead of the lightest ones. And so the take-home message basically from all what I just said is, should we think of mass as being a way for storing energy? Yes, mass is indeed a way of storing energy. And this is the physical principle that's currently being exploited in both fission and fusion. And I hope this introduction was not too long, but I guess clear and public to understand what's gonna.
Yeah, absolutely. I think it's very useful. So regarding the technical challenges, what do you see as the impediment that has slowed the process toward the development of the realization of a nuclear fusion reactor?
Okay. Yeah, going back to your initial question about the technological challenges. So indeed, this is a very, very good question, but not so easy to answer actually, because you might imagine all those challenges that the community can face in trying to do those kind of reactions. But we can spend almost a day citing all the challenges that are still on our to-do list, I would say. But let's try to get through them in a very, very simplified way. So let's start from the basics. I previously talked about the reaction that we need to achieve fusion, which is basically the combination of lighter elements into heavier ones. Now, a very interesting point about these reactions is that they occur in a state of matter known as a plasma, which is the word that I use in describing my field of research, plasma waves interactions. So half of it is about plasmas, actually. Now, what the heck is a plasma? So before answering this question, I would like Andrea to ask you a question, if you don't mind.
We can try, yeah.
Okay, so let's say that you have a solid like ice and you start heating it. And if you heat it well enough, what would you get?
Well, I mean, I guess if I put it into my body, the temperature of my body will melt it. right? And we get water.
Yes, so let's get to the liquid phase, right? Exactly. Right. So now, if you keep heating the water further, what would you get?
Sorry, if I do what?
If you keep like you got this water now.
Yep.
Let's say that you keep heating further. What would you get?
If I keep eating ice.
The ice that became water now.
Yeah.
Yeah. And now you heat this water. What do you expect?
Well, yeah. I will get the vapor, right? It will become gas.
Exactly. Exactly. Right. You get the
Three
gas
states of
phase, the
water. Yeah.
vapor.
Okay.
And now, if you keep heating even further this gas, what do you get?
I guess that question is for you. If I heat it again.
And this is where the plasma state
All
comes into
right.
place.
All right.
So
Oh, that's
plasma is
why it's in the
actually the
fourth
fourth
state.
fourth
Okay.
state of matter. And so, in fact, when reaching temperatures of the order of around 10,000 Celsius degrees, and that's probably why our kids don't know about this state of matter, probably, we get a new fourth state of matter, which is the so-called plasma state. And what happens in this state is that because of the very high temperature, the electrons of the atoms get detached and become free rather than staying bound to the atom itself. And so we end up getting a bath of positively and negatively charged particles, which is the plasma state and which is the fusion reactions are gonna occur. But not at temperatures of 10,000 Celsius degrees, unfortunately. In fact, for aiming to achieve the fusion reaction, we need to heat these mixtures at temperatures of the order of 50 million Celsius degrees, which is even higher than the temperature of the sun itself. And as you can imagine, it's
So
impossible
if you
to
get
be.
it, if you get it to the temperature of the sun, it wouldn't be enough to get the energy from it.
No, because we are on different conditions of temperature and pressure and everything. So if you follow a basic ideal gas law from very simple thermodynamics from the part of the public who might be expert about this, you do a quick calculation and you see that in order to achieve these reactions, you need maybe 5 times higher than the temperature on the sun.
Because the pressure would be too high. What's the problem with the pressure? If you can put it clearly.
It's just
What are the problems with the other variables if the temperature is not enough? Because
it's just different conditions, I would say. Like the conditions on the Earth are different than the ones on the sun, right? Like in the sun, you have complete vacuum, it's a space, while here it's on the Earth. So
okay.
you're never gonna reach perfect vacuum on the Earth. Well,
Yeah.
we try to reach a vacuum, but it's never gonna be perfect. It's never gonna be as much perfect as the one which is on the sun, basically.
Okay, this is so fascinating. I have to ask you a question. Has anybody ever reached in laboratory the temperature of the sun through an experiment?
In small labs, we kind of can get close to it, but not exactly. But in the reactors that we use for doing these reactions, of course, especially on the core, like on the periphery, it can get colder, but essentially it's the core that gets to these very high temperatures.
Okay, okay, that's pretty cool.
But as you can imagine, these plasma at 50 million Celsius degrees, it's impossible to put them in contact with any material that we have in the known universe.
Okay, that's clear.
Otherwise, the latter would melt, obviously.
Yeah, and I was thinking about, the investments that are needed to do this, and the fact that you're doing your research in Geneva, and of course the CERN as their
In Lausanne.
headquarters there in Lausanne, and
very
it's
close to
all in
Geneva.
Switzerland, right? And
Yes.
like, has Switzerland always had this certain attitude and continues to have this attitude to invest in this kind of research environment?
Like here at EPFL, at the Swiss Plasma Center, they got the TCV, tokamak à configuration variable, which is like one of the main research tokamaks in Europe. And I would say that the Swiss Plasma Center is one of the leading institutes in Europe regarding of everything related to plasmas and fusion energy. So I would say that it has been for quite a couple of years now, and it keeps growing and growing even further.
Okay, great. And in terms of research competition with the US, how is that position?
Okay, so in research, it's very well known to have these kind of competitions, but I would say that in fusion, it's more about collaborations, like because there are many collaborations between universities at the US, like MIT and Princeton and the Swiss Plasma Center. Like, of course, competition is always going to be here, but at some point, I think what matters most is the collaborations. And I kind of can see this here in this lab, actually, where there are so many collaborations going on with a lot of partners around the world, like either with the Max Planck Institute in Germany or with the Plasma Science and Fusion Center at MIT or the PPL laboratory at Princeton. So we can really see that there are people always trying to talk to each other and ask each other for advices.
That's beautiful. So you have some US colleagues there as well, I imagine.
Yes.
Okay.
I have a friend which is now doing his PhD at MIT as well.
Okay.
Fusion is one of these fields where it's very good to travel and meet new people and work at very prestigious and well-known institutions, which are currently leading the field, basically. And so I would say that traveling has always been like a very good idea. I really like traveling. At this age, it's good to like get out of your comfort zone and try to always meet new people from different cultures and try to get used to a new state of life, I would say. So my answer would be mostly yes, but we never know, it will depend on
Okay,
the
yeah.
flow.
I totally agree with you with having international experience, and I can only imagine how intellectually stimulating this experience can be for you. And if I didn't say it enough, like congratulations, because that's pretty much the top, right? So
Yes.
yeah. Um, I see your board behind you. It's some words, so not this crazy math, but it would be even more stereotypical if it was some crazy formulas behind you.
Yeah, you got lucky today. Today it was just some to-do list that I was trying to write on the
All right.
no
And
math for
regarding the investments for these institutions in Switzerland, the Plasma Center and the others, is the funding coming mainly from public institutions or private investors? Or both of them?
I would say both for sure, but I don't really know how these stuff are currently happening, so I wouldn't
Okay.
be able to give you details of these,
Okay.
but I would say that of course it usually comes up from both, like the private and the public sectors.
Great. And do you see the investments being high in other states in Europe, or is pretty much the biggest opportunities over 50% just in Switzerland?
No, sorry, I didn't really get the question.
If there are other centers of excellence for research in this field around Europe, for example, you studied in Marseille, right?
Yes.
And do they have any similar center in France or in the UK?
Yes, definitely. So in France, for example, where I used to study and where I also did an internship last year, I did it at the PIM laboratory, which is a laboratory part of Aix-Marseille University, which is also one of the very well-known labs for studying plasmas and fusion, even though it's kind of a small lab, but it still gathers a lot of amazing minds, I would say. And it's actually a very strategic site because it's very close to Cadarache, where you have the West tokamak in operation, and it's also one of the leading tokamaks in the world, and a lot of collaborations are always been undergone with people from MIT and from a lot of places in the world.
Super
And
interesting. So if anybody wanted to study your subjects in Marseille, you would advise for that?
of course, because it's a very strategic site, and you get to meet a lot of lecturers from this reactor. Actually, I've had a couple of lectures given by these people who actually touched the tokamak and went into the control rooms and operated the plasma, and it was really a good experience where you can like ask as many questions as you want, even if they can feel a bit dumb, but because for someone who haven't been in the control room, it's always very interesting to see how these stuff usually go in practice rather than just staying in the theoretical side of it. And so, yes, definitely, I would recommend it. And Marseille is a pretty city as well.
Yeah. I've never been in Marseille, but I come from well, for us it's the northern coast in Italy. So I come from Italy, but it's on the same side, just the Italian side, next to the
Okay.
Côte d'Azur. Yes.
Probably also have a very good weather.
Yeah. So do you think it would ever be possible or not to get energy at scale, like industrial level, from nuclear fusion?
Yes, I mean, of course, but maybe in order to, I would say maybe in order to emphasize this a bit more, maybe we can go back to the challenges if you want, because we can maybe talk a bit more about some other challenges that we face and which we are currently still working on achieving, if you prefer, and then
I was just curious about, sure, but I was just curious, like when you answer with a bit of hesitation, but then you say yes, of course. I like your optimism, and like why would you say of course, and how long would you think is realistic to expect?
like that's a very good question, actually, especially nowadays with all the fusion startups that keep arising day after day. I guess you've probably heard of them on the news and everywhere. And now, so far, the goal, I would like to say that the goal is still to demonstrate a net energy gain, to have an output power from the plasma higher than the one we actually need to pour into the machine. And this is what we refer to as the Q factor. So our goal is still to achieve a Q factor bigger than 1, like the ratio of the output over the input. And then after achieving this goal, one can start thinking about reactors that would actually be meant to deliver electricity to the grid, which would also prevent like other problems by themselves. But I mean, we all know that as a physics perspective and as an engineering perspective, we know that fusion can work. It just needs a bit of time in order to solve all the issues. But I mean, science has never been easy. We all know from the history of humankind that it has never been an easy task. But we all know that it's gonna work at some point. And then after achieving this net energy gain, we can start thinking about these commercially viable reactors that we actually call demo reactors.
So I like your optimism about the fact that you say that nuclear fusion is going to become a reality and we're going to achieve a nuclear reactor that we're going to get energy from, that we're going to be able to use it at scale. And I would like to understand better why you think that and what kind of a positive progression with time you have seen in order to say that.
That's a very fair question. I mean, we know that now, like one big step that we have now in our hands is that we know more or less how to design a reactor. So we know that we have 2 types of reactors, the tokamaks and the accelerators, and I might touch upon this a bit later on in this podcast. But so now we basically know what kind of reactors we have to focus on, what kind of approaches, what kind of heating systems that we need to use in order to heat this plasma, in order to achieve these 50 million Celsius degrees, right? And like we have many operating tokamaks around the world, either in France or in Switzerland or in the US rather soon with the Spark tokamak. But like one of the most recent achievements actually that happened in December 2023 was when they launched the decommissioning of the JET reactor, JET for Joint European Torus. So the decommissioning of a reactor, for those who don't know, refers to the process of safely closing and dismantling the reactor after it has reached the end of its useful life, you know. And
Yeah.
so basically, why is it an achievement by itself? Because JET has significantly contributed to the fusion community, with much of our current knowledge about fusion derived from the research undertaken on this reactor, and the foundation for upcoming fusion progress will be based on the advancements and insights provided by the JET reactor. And another very important achievement, actually, which also started rather in this period of time, is the start of operations of the new biggest advanced tokamak type fusion reactor after JET, the JT60 Super Advanced, located in Japan, which is a collaboration between Europe and Japan, whose role will be to unravel new secrets and to contribute to our expertise in operating tokamaks. So the rest of going lives, I would say that we have a lot of rattles in our hands, but of course we still have some mysteries to discover and questions to answer. But we're getting close. We're getting close.
Which is what you're working on, right? By the way, your research is working on this, so you have it on your shoulders, Mounir.
Yes, definitely.
We believe in you.
Like the whole community, we work every day, day and night to reach it, and we're gonna do it. We know that we're gonna do it. We just need the time, as in every science field.
Yeah.
And engineering as well.
Yeah, I never particularly liked the speculation about when something's going to happen, because there's multiple uncertainties that can happen. It's not a linear progression, of course. The evolution of science, as we know, it's quite bumpy. It's it's pretty much bumpy. So for different reasons. But does anybody at high level discuss about when is this going to be possible? Or is just express speculation that at scientist level doesn't make any sense?
There are some predictions mostly from the startups that have been arising like in the past few years, but I mean, most of them say that we're going to achieve fusion in 2030. I would say it's a rather optimistic expectation. Maybe I think by 2030, they mean like achieve the net energy gain. The net energy gain, yeah, it's possible that we're going to demonstrate the scientific viability of fusion maybe at the end of this decade, but making it commercially viable is another challenge by itself. And maybe a more realistic timeline would be maybe in about 20 years.
All right. Just for the public, if you could explain the net energy gain definition, it would be great. It would be useful.
Yeah, sure. So we know that basically the goal is to take energy out of these fusion reactions, which will be the output of that will basically be taken out from the plasma. But of course, for operating any kind of reactor, any kind of device, you basically need some input that you need to pour into the magnet system, into the heating systems that you need to heat the plasma to achieve these high temperatures. You also have some kind of power that you need to pour into the cryogenics, which are another very interesting structure. And so basically you have to put some power into the reactor, of course. But basically achieving some kind of output power would be meaningless if your input is higher than the output, right? So if you're putting into the reactor much more power than you're actually getting out of it, then what's the point? And so the goal is actually to demonstrate that our input can be higher than the actual input that we need to deliver to the reactor. which is the Q factor. So this Q factor is basically this input divided by the output divided by the input.
Yeah, is a number larger than 1.
Yes.
And it's currently at what level?
Well, so far it's less than 1, but like we have the ITER project, for instance. The ITER stands for International Thermonuclear Experimental Reactor, which will be the biggest operating plasma when it starts its operation. It's a collaboration between the European Union, South Korea, Japan, China, India, Russia, and the United States. And its goal is actually to demonstrate a Q higher than 10. And so,
okay.
Yes, but this reactor is solely for demonstrating the scientific viability.
Yeah, the scientific viability. So okay. And right now, how far are we from the 1?
That's a good question. I would say that we are maybe at about 0.8, something like this. But because the reactors that we had in the past, where I would say relative to ITER, they were a bit at a smaller scale, with maybe smaller magnetic fields, which can actually have an influence on the output power that you get out from the reactor. And so basically, with the knowledge that keeps progressing in terms of reactor design, increasing the size of the reactor, and getting new magnetic coils technology in order to obtain larger and larger magnetic fields, I think this is how we can enhance the value of Q that we can aim for.
Okay, great. I was thinking about the long tradition that Russia had in nuclear research, especially in the past. I don't know right now, but names like Andrew Sakharov and all of those guys that worked on hydrogen prototype. Like, and if anything interesting was going on there before the war, and something interesting has been able to come out of it from some scientists that wanted to do their research in the West after 2022.
Yeah, that's a very fair question as well, because so in fusion there are two approaches for fusion: the magnetic confinement and the so-called inertial confinement. Now, I would say most of my discussion has been focused on magnetic confinement, which is my field of expertise, and which is what the fusion community, most of the fusion community, is pushing for. It's pushing for magnetic confinement, right? And so for achieving this magnetic confinement, we also have 2 kinds of reactors that we can aim for, like the tokamak and the stellarator. And the tokamak design, tokamak is actually a Russian word, which, I've had a Russian colleague who taught me how to spell it. It's toroidalne kamera s magnitnimi katushkami, which basically translates to a set of magnets arranged in a donut shape. And so the Russians are the ones who actually initiated the tokamak design that we are currently adopting in our research. Well, it's a bit sad that they don't have their own one, but they are also part of the ITER project. And so, yeah, I would say that also one of the leading countries in the field, even though they don't have their own device.
Huge. So you mentioned that the Q variable, the output of energy over the input of energy for nuclear fusion, would be able to reach 10x.
10 is just for the kind of reactors that we are currently working on, which are just for demonstrating the scientific viability. But for the ones which gonna come afterwards, like the ones for the commercial viability of fusion, I would say maybe we can go a bit even further. But let's just focus
so
on
commercially, why would you go further? Why why can you go further commercially than you can in laboratory? I would think
No.
that in laboratory you can.
Maybe I must have been misunderstood. I mean, like, because now what we're doing so far is just for increasing our knowledge. But
Okay.
if we gain more knowledge, maybe we'll be able to achieve even higher Qs, because having higher Q is just can just be achieved in two ways. First way is either to have a bigger reactor, which is why ITER is so big. And the second way is to increase the value of the magnetic field that you use to confine your plasma, which is a second approach. So that this means that you can, let's say, build a smaller reactor, but if you have a higher magnetic field, you would be able to get almost the same Q that you can get with a bigger reactor. And so let's say you combine these two conditions. Well, maybe that's the plan for future commercially viable reactors. I don't know, maybe. But if you combine these two together with all the technology that we're still getting day after day, I would say that we can maybe increase this value of Q that we're aiming for. So the 10 is just the limit for, let's say, this decade, but nobody knows what's gonna be the
Sure.
decade after.
Why do we need the magnetic field in the first place?
Okay, I'll start from this. Right, so that's okay. So maybe before being able to answer this question, let's first start from the beginning. And the beginning is, why do we even need a magnetic field? I previously mentioned that there are two main approaches for achieving fusion: inertial and magnetic confinement. Now, I'm specifically gonna focus on magnetic confinement because it's my field of expertise. And not only, but it's also toward where most of the fusion community is pushing for. And so why do we call it magnetic confinement? Basically, first of all, what a confinement is. So basically, I told you that the plasma is going to reach 50 million Celsius degrees, which, if you put it in contact of anything in the known universe, it would just melt it. And so the approach is basically to confine the plasma. We say confine, it means that we need to put it as far as possible from the wall, otherwise it would just melt it. And this is not what we want to do. And so that's why there are two approaches for fusion. There are two different ways for confining the plasma. So I'm solely going to talk about magnetic confinement. So why do we call it magnetic confinement? Because it basically aims to confine this plasma that I told you about, to keep it away from the walls of the container of the reactor, basically by applying a magnetic field. So we know from basic physics principles that particles are gonna follow what we call gyro motion. So a gyro motion is basically a rotational motion, which means that the particles of the plasma are gonna rotate when we apply this magnetic field, and they will keep gyrating at a constant radius. And so imagine if the vessel of your reactor is a cylinder vessel, like this, for example. The rotational motion will be here in the inside of the cylinder. And so basically, because the particles are rotating inside the cylinder at a constant radius, this will keep them away from the walls of the vessel if the radius of the gyration is small enough, which is planned to be the case, don't worry. Now, here comes the second problem, which is, okay, the particle now is unable to reach the boundaries of the cylinder, maybe from the upper and lower sides, but can still move in the direction along the axis of the cylinder, and at some point reach the left and right sides, maybe. And that's why we follow the approach of closing the vessel to itself by adopting the donut shape, which is why we use the name of a tokamak, which translates to the set of magnets arranged in a donut shape. So, of course, in the scientific way is we don't call it donut, we call it a toroidal shape, but we can call it donut. I think it's much more interesting for the public.
Yeah, easy to
so
remember.
Here we go.
Yeah.
Having a donut-shaped vessel and producing these high-intensity magnetic fields, we just need to pour some gas, usually deuterium and tritium, which are essentially two forms of hydrogen, into the vessel and then heat it using very well-established heating systems, which are a discussion by themselves. And don't worry, I'm not going to go into the technical details. But if we use these very fancy heating systems, we obtain a plasma at about 50 million Celsius degrees. And this is the principle of magnetic confinement. I don't know if it was clear enough.
Yes.
I hope.
So,
Okay. So
after this great explanation, why then would you need to increase the magnetic field and how that would impact the performance of the reactor?
okay, that's what actually one of the startups in the US, Spark, is actually looking for. And so basically the fusion power is proportional to both the size of the machine and the magnetic field. The fusion power is basically the power that we get out of the reactor. And so you can increase this fusion power by either increasing the size or the magnetic field, which I might have previously mentioned, but maybe not into the details. And so basically increasing this fusion power can actually be achieved by either increasing one of these two, like the size or the magnetic field. Now, the influence of the magnetic field is more predominant, I would say, in a way that,
okay,
for example, what's Commonwealth Fusion is aiming for. Commonwealth Fusion is, or mostly referred to as CFS, is a startup, a spin-off of the Plasma Science and Fusion Center at MIT. And what they're aiming for is building a reactor 40 times smaller than ITER. So it's going to be much smaller. But because of the very high magnetic field, it can also lead to a Q of the order of 10. Like maybe ITER is going to deliver a power of 500 million watts. Well, that's the goal. Spark is aiming for 100 million watts. But just remember that it's 40 times smaller. So, you know, but basically because they're using a very fancy technology in the magnets called high temperature superconductors. And so if this happens to really be true, then this would be amazing because we will be able to have smaller reactors and still have not that much of a difference regarding the fusion power, you know. So that's why increasing the magnetic field is a very important case.
okay.
But of course, the magnetic field that's gonna be used on ITER is also not that small. It's still 5.5 Teslas, so it's not gonna be small at all. But because of this new emerging technology, the high temperature superconductor, we can even aim to higher magnetic fields, which is what Spark is gonna demonstrate.
Okay, this resonates a bit with me because as an economist, you know, when you study economic growth, you study that there are two ways you can increase an economy. One is the example with the pot. You know, the professor shows you a pot of a certain diameter, and it says you can cook more by increasing the pot. Like you have a pot that is, you know, 5 times the diameter, or you change the efficiency, what is called productivity in economics, and you change the way you either boil the water or the technology you've built the pot with, and all the materials, all the stuff in the middle. And so what that reminds me is about your thing is an increase in productivity. So it sounds, as an economist, you know, an economist, from your description, how I heard it, you know, they would opt immediately from magnetic confinement, because just doing, you know, the expansion expense linearly, but efficiency can improve exponentially. And so
Exactly.
okay, and so I'm interested about the other method you mentioned. Is it just a linear improvement? Like it just increases the output by, you know, a constant amount of the increase in the dimension of the reactor, or it is also some, you know, additional efficiency?
The increase of the dimension is like the fusion power has a linear dependence on the size of the reactor. But on the magnetic field, I think it's a square or I think it's a cubic relation.
So okay, so yeah, anybody who was a little bit of basics
I
of
might not remember
anybody who
might not
was
remember the
like in
exact
mind
exponent.
has done a bit of basic calculus should know for which one to opt.
Yes. But I might not remember the exact value of the exponent, but around this, I mean, this range.
Okay, and then why would anybody follow the other path?
You mean the increase in magnetic field?
No, the opposite one.
Because the high temperature superconductors are still an emerging technology. Like we still don't know much about these. Like not so many people know how to operate these. So this is actually a very new thing, and we still don't know whether it will actually be used in future reactors or no. So I would say we're just testing the idea and see how it's gonna go. But
Yeah.
yes, if it happens to be true, it's gonna be a massive milestone.
Okay, okay.
So, in science, you still just try new stuff out of nowhere, and then somehow they happen to match into the pieces of your puzzle, and then here you go. You try, okay, why not? And this, I think, happened to be the case with these HTS magnets, HTS for high temperature
And
superconductors.
I wanted to just follow up a little bit more on the comments you made, or just to get an idea, because a lot of people are in finance. If you read the Wall Street Journal, they're surely going to mention at least 2 times a week Sam Altman, and so it's a must, given the place where this interview is being conducted, just to ask you, um, what is it different about the startup he's invested in? Even if you have a little bit of knowledge, it would be just useful to touch upon it.
Yes, fair enough. Yeah, like private investments oriented toward fusion have constantly been increasing. I mean, and the one of Sam Altman is actually a very good example. So Sam Altman personally invested, I think it was $375 million into the Helion energy startup. So, we have plenty of approaches for achieving fusion, even magnetic confinement fusion that also has plenty of approaches. Like the major two are the tokamak and accelerator, but there's also other approaches like the field reverse configuration. And basically, the Helion energy company in the US is trying to adopt this approach, the field reverse configuration, which doesn't lie into the field of my expertise, but I know that it's a very fancy idea, I would say, to achieve fusion. And Sam Altman has invested into this approach.
You mean fancy because what do you mean by fancy scientifically?
Fancy because it's not the usual way, I would say. So
All right.
people are trying to do something a bit out of the box, which is very cool, actually.
It's
Well,
very cool. May turn out to be right or not, but okay.
exactly. But
But
the
that's
idea
not
is,
yet the main field you see research being developed in the centers of excellence in Switzerland. Am I right?
Switzerland, no, at least not yet. Maybe in the
Okay.
future, they might discover that field reverse configuration is actually the good path to follow, and then everyone is going to do it. We still don't know, but so far the focus has mostly been on other approaches.
Okay. Okay. Clear. Just as a final question, I come from Italy, and Italy used to have nuclear reactors before the Chernobyl accident in the 80s happened, in the 70s. And if you have a word toward the many people who are scared about nuclear, what would you say to them?
Well, it's true that we still have this mindset. I mean, from what happened in Chernobyl back in the days, and yeah, I would say this is one of the primary challenges that we face as nuclear scientists and engineers, like in trying to develop new ways and new technologies for the nuclear sector. But I'm not an expert of nuclear fission, but I know that the safety has improved by a huge factor. And so technically now it's almost impossible to have these kind of disasters again. I would say, like, it's almost impossible. But since I'm an expert of fusion, I can tell you that fusion is not gonna follow the same dangers as nuclear fission. Okay, people might be, I don't know, a bit more skeptical. Hey, we still don't know much about fusion. Maybe it might lead to some kind of disasters that we do not expect, and then boom, we end up in some Chernobyl 2.0. But one very important milestone for fusion was last year, and I think this will actually prove to people that nuclear fusion is a safe technique, relatively safe technique, and it will not have the potential of creating this kind of disasters. And this was when the US Nuclear Regulatory Commission Safety, the NRC, voted unanimously last year to regulate the fusion industry differently than the nuclear fission one. And this indeed will pave the way to much faster and simpler advances in terms of, you know, all the bureaucracy and the number of authorizations that you need to get. So, even though fusion is a nuclear process, it happens to be very different from fission regarding a reactor design. And that's why the NRC decided to take this decision. And specifically in a fission reactor, the entire energy content corresponding to several years of power production is stored within the core of the reactor. And it is this huge energy content that, okay, this might be able to lead to a meltdown. But as I remind you, now it's almost gonna be impossible, since now, like, we are, I would say, very good in terms of safety and everything. Like, even though I'm not an expert of fission myself, I can tell you that safety measures in fission are perfect, I would say. But on the other hand, in a fusion reactor, it does not depend on maintaining this huge amount of power in the reactor's core, like, because it doesn't rely on what we call the principle of the chain reaction. And so this means that you do not need to put a large sitting mass of fuel and to keep it inside your reactor for a year. Instead, the fuel is just constantly being fed into the reactor at a specific rate, allowing it to be consumed as needed. And so the result is that at any instant of time, the mass of fuel in a fusion reactor is very small, perhaps corresponding to the weight of several postage stamps, which makes the meltdown of any component almost impossible, which is what makes it impressive by itself as a nuclear technique, I would say.
Yeah,
this is
yeah.
the decision of the NRC. And this is also why people need to take a bit more attention on what nuclear fusion is actually.
Yes, I'm glad I briefly did, and I took the chance to invite you, because it has been extremely interesting. It would be a pleasure to listen to this interview. And thank you very much. I don't remember if there was any other point we would have liked to touch upon. If there's anybody you would like to add, otherwise, it's been great.
I think it's okay from my side.
All right, perfect. Mounir, all the best. Thanks for what you're doing, because I believe, you know, every job is a service to society, but what you're doing can pretty much change a lot of things. So
definitely.
So I really appreciate it, and I mean, I hope to see you again in the future, and all the best.
Of course, thanks a lot, and fusion is coming, guys. That's the
all right.
message.
Let's go. Thanks, Mounir.